This is the first of two videos about shifting equilibrium. In the last video, we talked all about equilibrium and the equilibrium constant and how that value relates the concentrations of the different pieces together at equilibrium. And in this series of videos, we're going to talk about non-equilibrium conditions. We'll talk about how to use Q instead of K, Le Chatelier's principle, the different types of stress we can add to a system, and how the effect of temperature is relevant. So we talked all about what the situation looked like at equilibrium, but what if we're not at equilibrium? Because we're not always there. Sometimes the system is stressed or changed, and it's bumped away from equilibrium, and it has to be on its way back. So if we're not at equilibrium, we cannot use K. We cannot use that equilibrium constant. So we need something else. We need a new expression to relate the concentrations of the different species. And so what we're going to use instead of K is going to be Q for quotient, the reaction quotient. And that is our non-equilibrium expression. So this expression Q, similar to K, represents how much of each species is present at any point. So remember that our K related the amounts of species only at the equilibrium, and Q relates the amount of the species at any point in the reaction. So let's throw up the formula here for our generic reaction. A plus B goes to C plus D, with Mn and X and Y being the coefficients. If we want to write the expression for Q, we are going to do products over reactants, just like we did before. I will do concentration, so that's technically going to be Q sub C. And the formula looks the same. So we have the concentration of products with the coefficient as a superscript over the concentration of reactants with the coefficient as the superscript. So what we're seeing here is that this is exactly the same thing as we did before. So the QC and the QP, they're calculated exactly the same as we did for K. Same as KC and KP. So it's the same expression, but it represents something different. One of them represents the concentrations at any point, and one of them represents the concentrations at equilibrium. Now, of course, whenever a system is not at equilibrium, it's always going to be going back. So how does the system return to equilibrium? From wherever it is. It's like a homing beacon. You always return to home. You always return to equilibrium. So how does the system get back to where it wants to be? So we can use Q to tell us about how to get back to equilibrium. So Q is like your starting location. It's like your current position. If you were using your phone and trying to do a navigation, it would look something like the "you are here" symbol, like the crosshairs that mark your spot on the GPS. So Q tells you where you are, and your K tells you where you want to go. It's your destination. And on Google Maps, the destination looks kind of like a hot air balloon. Something like that. So you have to figure out how to get back to the equilibrium, how to get from your crosshairs position, you are here, to your little hot air balloon destination that you're going. So to return to equilibrium, we need to shift the concentrations until Q equals K. All right, that's important, so we're going to give that an underline. So that's what we're trying to do. We're using our Q, which tells us you are here, this is where you are in the system. We're identifying K as the destination where we're trying to go, and then we're going to watch the system shift to move Q until it equals K. And so the way that that shift happens was described by someone named Le Chatelier. So it is called Le Chatelier's principle. So Le Chatelier's principle says there's a three-step process. When a system is given a stress, something that changes the system shifts to relieve the stress. And it reestablishes the equilibrium. Okay, so there's three parts of this definition. So the first step is the stress. Something happens to the system, something is added, something is removed, one of the conditions is changed, and that moves our Q away from the equilibrium. It moves our current location to somewhere else on the map. When this happens to the system will shift, step 2. So it does something, it changes itself to move Q back to its destination, back towards K. And when Q equals K, that's step 3. We've reached the equilibrium. So I like to try and describe what this shift looks like using a balance beam. So let's draw what that looks like for a generic reactants goes to products reaction. And so the reactants, the way we've drawn this, the reactants are on our left side and the products are on the right side. So we're going to call it shifting to the left or shifting to the right because that's easier to write. Okay. So let's think about if we took a system and we added a stress to the left side. We'll talk more about what a stress looks like in the next video. So if we add a stress to the left side, we can think about this side sort of becoming heavier. And the way we like to talk about this with a balance beam, we think about K as being the fulcrum, being that center point of the balance beam. And then we think about the balance beam being weighed down on the side with the stress. So if the left side is stressed, we're going to be weighed down on the left side. And that stress tells us where Q is. So Q is going to be on the stressed side. So if we add a stress to the left, that means Q is going to be less than K. That's what the balance beam is supposed to represent, sort of like a number line. Q is lower than what K is equal to. And so if we experience this stress, the system is going to shift to relieve it. So that means the system is going to shift to make the balance beam flat again. So it's going to push towards the right. So we're going to say it shifts to the right. And after it shifts to the right, it returns to the equilibrium. And so we can draw equilibrium like this. We can draw our balance beam with K in the middle, and we can draw a balanced looking balance beam where Q has returned to the center. That's our equilibrium step. So this is a picture of at equilibrium. And at equilibrium, we know that Q equals K. And there's no shift that happens here. Okay, let's look at what happens if we stress the other side. So if we added a stress to the product side, so we'll add a stress to the right side. We'll draw our balance beam with K in the center, and if we added stress to the right side is going to be lower, and that's where our Q is. So we're pushing down on the right side. So our Q is going to be greater than K in this situation, and the system is going to respond by pushing back in the other direction. So we push back towards the left. Shift left. Okay, so these are our three situations. So if we can shift to the right, push Q to be larger. If Q is too large, we can shift to the left until we reach our ideal situation where Q is equal to K. So this is kind of like if you get punched, you punch back. That's what the system is doing. Something happens to it and it's reacting in the opposite direction to relieve that stress and return to equilibrium. So in the next video, we will talk about the different types of stress to a system and how those will each affect the Q value.